thing I noted as I was preparing for class was that the lecture says that we were supposed to have done gravity on Wednesday, and today was supposed to be fluids. So I have ground down a little bit too slow in this material, which means that we'll have to be adjusting a little bit what we're covering on what day. But we will keep the test the same day, so I'll cut a little out of my physics stuff so that we can get the physics done and move on to chemistry at the appropriate time. So I just want to make sure that I mention that rather than you being like, I'm not sure where we are in this schedule, but you know. And so homework, we're not going to have homework covering stuff that we didn't cover. So it's going to be mostly from chapter 3. On Monday, I will talk about fluids and thermodynamics. And what I talk about Monday would also be on the homework, but not other. Hello, Leslie.
That's helping a preview day students find their class.
Okay. That is a good thing to do. Okay, so with energy, we've been talking about potential energy. Now, I had to correct the word for one person. Potential energy is defined as the ability to do work because of its position or configuration. I may not have said configuration clearly because I don't remember what the word was the students wrote, but it wasn't configuration. It took me a minute to realize what they meant. So potential energy because of the configuration. So here's some examples. What's the one that we have used, not these three, but the one that we've already used about potential energy? The example for something that gives potential energy. Gravity. I just assumed that was what you said. It sounded like to me, Gabby. So gravity gives us potential energy, but other things, if you use a bow and arrow, you pull back on that bowstring, the string is not what's stretching. What's actually bending? If it's not the string, it has to be the bow. The bow is bending, and so it's deforming, and because of that bending, it's storing energy, and when you let go, the bow is going to spring back, pulling the arrow by way of the string. And so you have potential energy stored in the bow when you pull back on it. A stretched rubber band, you're stretching that rubber, it's elastic. Elastic actually means when you release it, it'll come back to where it was. The last one here, the raised ram of a pile driver, we have some pictures with it. What's not mentioned there is one of the most ubiquitous things, a spring. A spring is also something that's elastic. If I stretch it, it will have a force to pull back. And because it has that force to pull back, it will do work. I did work to stretch it. I had a force I applied in a distance. When I let go, it will return with its force over that same distance and do the work back. So it stores energy and then releases it when you let go. So these are all examples of items that will store potential energy. So I'm adding the gravity here because we'd already done that one. That pile driver is an example of gravity. So for gravity, the potential energy is mgh. We've already talked about this. Look, I have a pile driver again. Apparently, I'm really into the pile driver thing. Example I used in class on Wednesday. What's easier, to raise something by, I said, taking it up the steps or up a ramp, because I had a picture with steps and a ramp, or to lift it? It's going to be a lot easier to push it up the ramp as long as the friction is small. So if we have a low friction ramp, we can do the work of getting it up there in an easier fashion. We call something that makes it easier to do the work a simple machine. So that ramp is a simple machine. It makes it easier for us to do the work. Do we still do the work? Does she still get that block from the bottom to the top? Yes. And so she still had to apply a force over a distance, but it was a longer distance that she had to apply it and a smaller force, which is why it was easier, because it was a smaller force. Now, the work energy theorem is really important in physics. The work energy theorem, I said energy is the ability to do work. And so now we get to that actual relationship. And the work energy theorem says that the net work is equal to the, what does that symbol mean? Change in. Just have to make sure that I don't just say words, write things, and you're like not seeing the connection. Change in KE. Any idea what KE is? Kinetic energy, energy in motion. So the net work is the change in kinetic energy. So if I do work on something, if the net work, notice it's not just the work I do, it's the network. So if I do work on something and lift it up, and gravity's doing work on it that's negative, the network might be 0, which means it'd be constant speed. But if I do more work on it than gravity, then it's going to be going up. And, it increases upward speed. If gravity does more work than me, it'll increase its downward speed. So the net work, the sum of all the works, is equal to the change in kinetic energy. And so an example here, this dude is, I don't know how he's hitting the brakes when his feet are up in the air, but nonetheless, he's hitting the brakes to try to avoid going over that cliff. He must have hand brakes, I guess, or maybe apply the emergency brake. And so there is a work being done because there's a force of friction acting like that on the tires. And he's traveling a distance, d in this direction. Is the force of friction doing a positive work or a negative work? They're opposite directions for the distance traveled and the force. That's negative. If the force is opposite to the direction it moves, it's a negative work. And so this is a negative work. And according to the work energy relation, that's equal to the change in kinetic energy, which is the kinetic energy final minus the kinetic energy initial. If he's not going to go over the cliff, what's his final kinetic energy going to be? Since kinetic energy is 1/2 mass times speed squared, then he's going to have the final kinetic energy is 0 if he doesn't go over the cliff. His initial kinetic energy, notice kinetic energy is always 0 or positive. We don't have negative masses, and speed squared is always positive. So minus kinetic energy initial is going to be a negative value. Our work is negative. It works out. It's kind of important that those signs. If you slow down, you lose kinetic energy, so that's a negative change in kinetic energy. So we needed a negative work done on it to lower the kinetic energy. Leslie has a question.
So what were we looking for in doing this problem? The work?
We weren't looking for something that wasn't given as a problem. We were just identifying the relationships. So what we were identifying was, first we started with identifying what the work is. Force times distance, and because they're opposite directions, that's why there's the minus sign. And then we said that should, according to the work energy relation, be equal to change in kinetic energy. So then we looked at the kinetic energy relation to see how that could be.
That's kinetic energy final minus kinetic energy initial? Okay.
Right, the change in kinetic energy is final minus initial. Now here is your actual introduction to the kinetic energy equation. I wrote the equation on the previous slide, 1/2 mv squared. We talked about it in the lab yesterday. By the way, Alex took too much blame upon himself for the grading problem. We're learning this new grade scope thing, and it can either do a additive or subtractive grading. And so what we've been doing is subtractive. We just say you did it right and you get full credit, or you made this mistake and you lose points. But the last two problems, we, not him, because I was the one who set it up, and then he had to change a bunch of them, and he didn't change the last two, but I was the one who set it up. Didn't change it to subtractive, and so it gave you all 0 unless you made a mistake, and then you got points for making mistakes. So that's why everybody's scores were lower. And so we reversed it, and everybody's scores should have jumped up by somewhere between 15 and 20 points on that. So, yeah, because I didn't look at them. He said the scores are a little low, now we know why. And so there should be some relief there, I think, scores. I don't know if they've made it to Moodle yet. I think he's updated it, but if not, they will. In lab yesterday, we were using kinetic energy. So we're using this 1/2 mv squared, which is why I talked about it. And just like with momentum, things with more mass are going to have higher kinetic energy. Things with more speed are going to have higher kinetic energy. But unlike momentum, speed is more important than mass. With momentum, they were equally important. It's mass times velocity. For kinetic energy, it's 1/2 mass times the speed squared. So if you double the speed, what's going to happen to the kinetic energy? It's going to go up by 2 squared, which is 4. So doubling the speed quadruples the kinetic energy, whereas it only doubles the momentum. Nice. That's supposed to be there. No further work is required is the word that's there. So if you are lifting weights, so this afternoon I'll go to the gym and go down, way down, take that bar, try to press it up, right? If I get halfway and it stops, I can sit there for probably a good 2 or 3 seconds before it comes back down. And am I doing work on the bar while I'm holding there at a set height? No. I'm applying a force upward, right? I'm applying a maximum force to try to get it to move up. But if it's not moving, I'm doing no work on it. And so what's happening to its potential energy if I'm doing no work on it? If it's sitting there stationary, what's happening to its potential energy? Okay, it's at rest, so kinetic energy is 0, and potential energy is going to, it's actually just going to stay the same because there's no change in the energy. It has to go up or down to change its energy. Now, my muscles will fatigue after a few more seconds. They're obviously going to be very fatigued when I can't push it up. And so then it starts coming down. Now, I'm pushing up, it's coming down. Am I doing a positive or negative work on it? Negative work, that's right, because the motion is opposite to my force. What about gravity? Is gravity doing a positive or negative work on it? A positive, because gravitational force is down and it's moving down. What's happening to potential energy when gravity is doing a positive work? It's decreasing, because it's converting potential into something else. So it's converting that potential energy into working against it. Now, if it comes down at constant speed, that's kind of good, because then it doesn't crush me. Yeah. And in that case, the work that I did, which was negative, would be exactly equal to the work done by gravity, which is positive. If my work is smaller than gravity's work, it's going to come down harder. I have to admit this. A couple of weeks ago, we went to Christmas break. I didn't work out for just 2 weeks. I came back and I was using a weight that should have been easy. Still not easy. It's getting easier. And, first set I did 8. Second one, I only did like 6. Third one, I got to 4. I was like, I can do 2 more. And it turns out I couldn't. This is right after Christmas. There's only one other guy in the gym, and I didn't want to say, "Will help, will help." So I did the really shameful thing. I rolled it down my body. Don't ever do that. It hurts. It's better just to dump the weights. I never put the little clips on the end so you can dump the weights. You just tip sideways, and they fall off on one side, it makes a big clang, and it goes the other way, and you're free. But it makes a big clang. It's embarrassing. So I rolled it down my body. It was painful. The guy saw. I came over. You can always ask for help. Yeah. So anyway, here's the pile driver. I mentioned it twice. Now we can look at the pile driver. What's going on in the pile driver? First, you use this little winch. The winch is a simple machine. You might have a weight there that is 1,000 pounds. And with that winch, if your handle is longer than the size of the roller, then you're going to be doing more work. It's actually torque. We're not going to have time to talk about torque. But you're going to be applying more torque than a bigger torque for the same force. So you're able to roll it up because of the simple machine of the winch. So you get it up there, you did a bunch of work, The work you did on that mass is going to be equal to its change in potential energy. And then you cut the string and the mass falls. What's happening to energy when you cut the string? We had potential energy up here, but no kinetic energy. What happens to that energy as it is released? Well, as it goes down, what happens to potential energy? Okay, now that is where I was going for. But the potential energy, as you go down, the height is going down, so the potential energy is dropping. And so one of our fundamental rules in science is energy cannot be created or destroyed. It can only be transformed. When I do work, I'm taking energy from somewhere else and moving it. So we talked about I eat food, that's how I get energy in my body. My body then metabolizes that energy so that I can do the work. So that energy is coming out of me, goes into that thing, goes into gravitational potential energy, then it drops and goes from gravitational potential energy into, I think it was Ivy that said, into kinetic energy. So as it falls, the potential energy drops and the kinetic energy goes up. Well, of course, the mass stays the same, so the speed is rising. So it's going faster as it falls. And so when it hits this, I don't know what to call that, stake, it hits it going really fast. It has kinetic energy, which means it has the ability to do work because of its motion. So it hits that stake, it's going to do work, it's going to apply a downward force on the stake, and the stake is going to move some distance so that the kinetic energy of that mass is transferred to the stake and does work, pushing the stake into the ground. So we can explain the whole system of driving the stake into the ground using our understanding of work and energy. So I've already talked about this. I'm going to move on. Let's answer 2 questions and do our first demonstration. So question number 1. Setting the reference point for height as the lowest point of its swing, so where it is right now for this bowling ball, what kind of energy does a pendulum have at its highest point? So does it have kinetic energy, gravitational potential energy, spring potential energy, or chemical potential energy?
That's because the session doesn't exist.
Oh, that's my mistake. You're right. Okay, let's start over. Escape. Close this. Don't save. Oh, I feel silly. Don't save. Start the session. Thank you for telling me rather than being frustrated for a while. I mean, we would have figured it out before the end of the question, but the earlier you tell me, the earlier we get it straight. Yes, but now I have to reopen the... All right, you may answer now. Rachel is the first one in, then Leslie, then Gabby, then Danny, then Sam, then Ivy. Still missing Mariah and Ashton. Ashton, just Mariah. Okay, and Mariah, I now have it set so it understands that that's your clicker, just in case you're wondering. And of course, we have the problem that it did not show me what you answered. What it did is it actually comes back to the same question I see. Try answering again. See if it tells me the second time. I'm learning. So, Sam and Mariah. This will be good information to share about what's going wrong. I definitely learned. Okay, still waiting for Sam and Mariah to answer a second time. There goes Mariah.
It says no link up on channel.
Really? That's not perfect. Okay, I'm going to go on. Okay, there it goes. So we had Oh, that's excellent. Excellent. Oh, yeah. Okay. What we answered was the second question. I was like, what in the world? It went to the black screen. Now I know what happened. Yeah, learning, like I said. So we answered 0, 6, and 2 unless anyone reread and saw that it was a different question the second time. It was the same except for one word. So let's just stick with this one. 6 people said it has gravitational. 2 said spring potential. Now, the answer here is pretty simple. It's gravitational. There's no spring involved, so it doesn't have spring potential energy. It has gravitational potential energy because potential energy due to gravity is mass times g times height. Spring, it's actually 1/2 the k, the spring constant number that tells you how stiff the spring is, multiply that by the amount it's stretched squared. Okay, so here's the second question that you were supposed to have. Let's go ahead and play with this just to talk it through. So I have this simple pendulum. I bring it up here. We just discussed what kind of energy does it have? Gravitational potential. Now here's the difficulty. You're supposed to do this and have the length and everything adjusted so your back's against the wall. If your back's against the wall, you just keep it pressed against the wall and you know you don't lean forward. Here I have to trust that I won't. If I let go from here, what's going to happen with energy? Well, the first thing, as it starts to fall, what happens with energy? It goes from gravitational potential into kinetic. So the second question was, what kind of energy does it have when it's swinging? So I let it go and it gets down to this point. It's converted it all from potential to kinetic. So all the energy's gone from potential energy to kinetic, comes back up here, and what's the energy doing? It's going back to potential. So if I let go, and once again I have to make sure I stand up straight and don't lean forward. So I let go, it swings over and comes back. How high is it going to come compared to where I let go? Okay, a little lower, she says. Do you have a reason for that?
No. Kinetic energy is
Well, first let's do it. Let's see. And so we hope that I didn't change my angle. Okay, so it is a little bit lower, right?
Yeah.
If I lean forward a little, I could have added to my cheeks, started my chin. So ideally, introductory physics class physics says it should come to the same height because energy cannot be created or destroyed. It's just shifted between one type and another. So it started with potential energy, converted it to kinetic energy, converted back to potential energy. When it comes to rest, its kinetic energy is 0 because 1/2 mv squared. It should have the same potential energy it started with. And so it should just go from the same height down, back up again, back and forth, back and forth. But Gabby said, no, it's not going to go quite as high. Was it you, Gabby? Okay. There's a reason it didn't go quite as high. It's the same reason that when you had the cart going down the track, just a single cart, momentum wasn't conserved perfectly. It dropped. Why did it drop? There's some friction on those tracks. Well, there's some air resistance. We know I don't know about you guys, but me as a kid, when we were driving from like Modern Day Academy to Santa Cruz, I would have my hand out there going, wee, playing in the wind, feeling if I go like this, it's got a strong force, like this, it's smaller. That air resistance. The faster it goes, the bigger the air resistance. But if something's moving, there's always some air resistance. And so that air resistance is transferring energy from this into the air. The energy wasn't lost, it was only lost to us. It went into the air. So when we talk about mechanical energy, the mechanical energy is the energy that we can use, right? It's the potential energy, the kinetic energy, and we don't count what actually is kinetic energy, the air molecules there, but that's where it was going, is making the air molecules move. So, I don't know, you've probably seen demonstrations like this all over the place, but it's one we love in physics. I don't know what happened here. Okay, very quickly about machines. Actually, before I do the machines, let me just do a couple more demos. I love my demonstrations. So let's start with this one. This is a bunch of rubber balls, super balls. And if I drop the super ball, it bounces up. Now it doesn't bounce all the way up to my hand again. It only bounces about 60 to 70% of the height that it started with. Maybe even less, 50 to 60%. So what does that tell you about the energy? If it only bounces up 50 or 60% as high as it started, what's happened to energy? It went down. Where did it go? Okay, some definitely went into the air, and some was lost when it hit the table. It deforms, and that deformation is going to have some loss always. So now I have 3 such balls that are on this so they can't leave. They're just stuck together. And then this ball that can leave. And I'm going to drop them as a set. And it's going to hit the ground and bounce. Now only the red ball will be allowed to leave. The others will bounce off the floor, but they're stuck together. What do you think is going to happen when it hits the ground?
They're going to bounce awkwardly.
Bounce awkwardly?
Sideways, maybe?
So will it come as high as my hand?
Oh, no.
Go lower, go higher?
Lower. Yeah.
Close. It kind of shot off of there, didn't it? It's right here. That's like the best I've ever done. Because you have to drop it vertically. If you drop it, it goes sideways, it shoots off sideways and everything. So this ball, what happened to its energy after the bounce? It went way up. How is that possible?
Because the energy involved. The potential it went up.
There were multiple people answering, and I'm sure more than just Gabby was correct, but I heard Gabby clearly, and she was correct. So we had kinetic energy, well, potential energy in all of the balls. They hit the ground. When they hit the ground, they all converted to potential. The bottom one hits first, and it sends a shock wave through it. And like the top of this blue ball doesn't know that the bottom has hit the ground until that shock wave gets to the top. So the top was still moving down. And then when that shock wave gets to the top, then the green one gets hit by the top of the blue ball, and the shock wave continues. And what you actually end up doing is transferring energy from each successive ball into the one above. So most of the energy of all of the balls was transferred to just the red ball. And so because it transferred all the energy from the other ones, it ended up, see, that's what usually happens. And then you're like, wah, wah. And so the red ball goes shooting off because it has most of the energy. Now, you can do this like, okay, so Danny's on the basketball team. You can just take like a tennis ball or a volleyball and a basketball, hold them together and drop them as one, and the ball on top will go shooting off because of the transfer of energy from below.
We even do it with 2 basketballs.
Okay, not done it with 2 basketballs, but
We had it happen last night. Accidentally, they got stuck in the net, and when they came down on top of each other, and they hit one.
so cool. So Danny's like, yeah, I seen this one. Saw it last night. Okay. Now this one here is just for fun. It's talking about bouncing. So I have 2 balls here. And so I take these balls to my friend Leslie, and I say, look at the balls. They look the same or different?
They look the same.
They look the same. Squeeze them. They feel the same?
Yeah. This one feels maybe a little. They feel the same.
Okay, one feels a little mushier, but they feel kind of the same. Now, to see if they're the same, I'm just going to drop them both. Not at all the same. I had her feel it, and she was correct. One is mushier than the other. One of them, this one here, when you squeeze it and let go, it comes right back with your finger. This one, you squeeze it, you let go, it kind of stays for a little bit. So when they hit the table, the one that stays for a little bit, it absorbed that energy and didn't return it. The one that comes back, springs back, returned the energy. And so the one that springs back bounces, the one that didn't is just dead. So we have the coefficient of restitution, something that tells us about how springy the balls are, tells us how well they're going to bounce. if it's what we call perfectly elastic, what we just called elastic yesterday, it will return all of the kinetic energy. So, hint, a day late. What you should have found in lab yesterday was the elastic collisions, your kinetic energy was conserved within the loss due to friction. Whereas the inelastic ones, those are the ones that deform and don't give back the energy. They absorbed some of that kinetic energy, so it wasn't conserved. So what you should have had, hopefully you had, I know I was looking at data with a couple people, it wasn't that way initially, but I know redid it and got the right answers the second time. You should have got that momentum was conserved in all of your trials because you just had that low friction and we would take that into account saying it's conserved, it stays on the slope dictated by friction. It's not perfect because if one's rolling and then two's rolling, you really double the friction. So it's not perfect, but it's the best we can do. And we focused on just before and just after so we didn't have much effect from it. So all of them should have had momentum conserved, and it should have been all of the inelastic ones where they stuck together, momentum was not conserved, and all of the elastic ones it was. But you could have some, some variations, like if they're going the same speed toward each other, the total momentum is 0, and you might see just a slight shift, and it looks like a huge shift because total momentum was fundamentally 0 before, fundamentally 0 after, and your error may be large compared to the total value. So you might have seen a little bit of variation. This is my last of my fun tricks for the day. This is half a ball. So I take this ball and I turn it inside out. And I put it on the table and I stand back. What happened there? Okay, it went up, but why did it go up? Because that's right. It has to be that answer. Understanding why is a little more complicated, but it has to be that potential energy was converted to kinetic energy. Did you have an answer, Brian?
I was going to say, because the kinetic energy goes down.
Okay. What happened here is I did work on it, right? I inverted it. I had to put a force on it. It doesn't just do it itself. I had to put a force, moved it a distance. I did work. That energy is now stored in this. Now it's sitting there. It's storing the energy, but it's not very stable. So after some time, and we never know how long the time's going to be, it will snap back, returning all of the energy that I put in, or almost all, when I deformed it, converted it to kinetic energy, and so it'll go boom. And we know it'll happen sometime. It's more fun to have to wait, right?
No.
It is. Okay. So conservation of energy is what we've been seeing. Energy is conserved. It's not created or destroyed. It's just transformed from one type to another. Right now it has potential energy. Has potential energy because I didn't work on it. I transformed potential energy my body had, stored as fat, or the glucose flowing through my bloodstream, transferred it to that doing the work, so it has the potential energy. So this law of conservation of energy is actually the first law of thermodynamics. The first law of thermodynamics says that you cannot create or destroy energy. You can only transform it from one type to another. And you see here I had ball demonstrations, so I'd remember to do these demonstrations and not go on and say, oh, man. Huh? No, not yet. It will. Let's go past this. The simple machines, things that allow us to do work with a smaller force. No machine puts energy in. It only is allowing us to transform energy from one type to another. And the best you can do is have the mechanical energy out is equal to the mechanical energy in. In reality, usually you're going to have some loss. That is something like friction that's taking away mechanical energy. So let's look at different types of simple machines and how they work. So our first one here is just a lever. So how do you make a lever? You take a stick, and you put that stick on a fulcrum. So this here is my fulcrum. Now, it's not a great fulcrum. Let's see if I can find a better fulcrum. Yeah. Going with no, not today. So it's on a fulcrum. Now, if I want to lift something with this stick, like let's say I want to lift this remote control. If I put the remote control here, it's like a teeter-totter, and the remote control is now holding that end down lower. Why is the remote control not on the ground?
It was more of a force on the right one because it was like longer on that side, and now you're adding another force to the other side to kind of stabilize it.
Okay, this entire meter stick has weight, and there's a lot more weight on this side of my fulcrum than on this side of the fulcrum. So right now the weight of the longer side is holding that down. I put my remote on the shorter side, and now it comes down, and it's just about perfectly balanced. So I have the weight over here that has to do with the distance as well. And the weight over here with the distance makes it balanced. What we're actually calculating here is called the torque.
So does it have anything to do with force or just weight?
Oh, definitely has to do, weight is a force.
Okay.
Now notice this equation. Torque is force, that little upside down T, that means perpendicular. So the torque is the force perpendicular to the distance. Now I just have to relate the story because I always found it so funny. When I was a kid, my dad and my Uncle Jack, not the Jack Webb, but a different Jack Webb, were talking about cars. And they were talking about, I think it was a Mustang, yeah, that engine's got a lot of torque. And little, 7-year-old Richard's like, Daddy, what's torque? My dad digs for me. He says, well, it's kind of like the amount of twist. And little 7-year-old Richard was smart enough to say, well, not smart enough, precocious enough to say, I don't think Daddy knows what he's talking about. I didn't say it out loud, but I was like, okay, he says torque is the amount of twist. That doesn't make any sense. It's got to be something else. He's not sure what it is. Well, it turns out that my dad was pretty much correct. Little 7-year-old Richard wasn't as smart as 7-year-old Richard thought he was. We'll talk later about little 7-year-old, or maybe we won't, little 7-year-old Richard watching Uncle or Cousin Rob shoot a gun, and yeah. Anyway, let's not talk about little Richard. Little Richard. Anyway, little Richard is an Adventist, right? Yeah. I mean, he gives people, anyone who comes to visit him, he makes them take a great controversy home. He went to the seminary. He went to study religion at Oakwood a couple times. Stopped his career to go study to become a pastor. But of course, a lot of his lifestyle was not consistent with Seventh-day Adventist beliefs. Funniest story, of course, I know is my own sister. Back when I was in college, he was the minister of music at the Kansas Avenue Church, a church in Arlington, California, Riverside, basically La Sierra area. And my sister went to the college store, and there was a limo there. And she was like, oh, this is cool. So her and her friends go check out the limo. And this big black man opens his door and says, you guys want to come in? Yeah, sure. And so they come in, wow, this is cool. And my sister says, yeah, who are you? He says, well, who invented rock and roll? And my little sister, being the brave one, is all, Elvis? And little Richard gets mad. No, I invented it. Little Richard invented it. And yeah, that's our encounter with little Richard. Yeah. Anyway, back to physics. It was important. It helps you remember nothing. But so torque is a twisting force. If something has more torque, it's more able to make things rotate. And so for your car engine, the more torque it has, the more twisting force, the faster it's going to be able to accelerate. Remember Newton's second law. The acceleration is the net force over mass. Well, the angular acceleration, which is how rapidly it starts to rotate, is equal to the net torque divided by something that's equivalent to mass. And so if you have a car engine with more torque, it's going to be able to make things rotate faster, which means you leave that stoplight, you can make your car go faster if you have an engine with more torque. Different from power. Power is how quickly you can convert energy. Torque is about how quickly you can accelerate. Yeah.
So then how, you're talking about twisting, how is that related to?
Okay, how's that related to this?
Yeah, because you said it has torque, but I don't see any like actual twisting.
Well, there is a twisting from between this to this. And so let's go on with this then. So torque is the distance perpendicular to the force. So in this case, if we look at the side here, the distance is going from here, well, on the short end, there's my distance. And then the force isn't perfectly perpendicular in that picture. It's pretty close to perfectly perpendicular here. But the force and distance are parallel. The distance is not the distance traveled. It's the distance from the pivot point to where the force is acting. We call that distance the lever arm. So if I put the force at a larger distance away, it creates a bigger torque. So we can make a practical example. I used to have some big masses I kept here for this. Big masses because it makes me feel strong to hold a big mass out here. I hold this out here. This is a small mass. It has a torque. It will make my arm rotate. If I release my muscles, what's my arm going to do? It's going to go like this. So that torque that was caused by this weight at this distance makes my arm go like this. If I held it out half as far, it doesn't make it rotate as hard. So I have more torque when it's farther out, less when it's closer in. If I put it over here, which way does my arm rotate? Clockwise or counterclockwise? It's going to rotate clockwise. If I put it over here, clockwise or counterclockwise? Counterclockwise. So we have a different direction for the rotation, hence a different direction for the torque based on which direction I hold it out. So torque is a vector. It has a direction. And we call counterclockwise positive and clockwise negative. So with this, I took my lever apart to use this as a mass. So with this lever, now I've changed the lengths, not by much, but you can see it's hanging down a little further. It's because of angles and whatnot. Let's not get too lost on that. If I want to raise this, I put a force here. I need to have the torque that I'm creating equal to the torque over here. How's the force I have to put here compared to the force there? Would it be the same force, a bigger force, or a smaller force? One of those two. Huh?
The force that you have to put on there?
Yeah.
Smaller than the other side.
It can be smaller here to do the same lifting, right? Smaller than the force would have to be to do this. And the reason is because I'm going to have a torque balance. I'm going to go like this so it, like this, the weight there is playing to hold it up. That doesn't do me much good. There. Now that weight holds it down. I go like this. Doesn't take much force here at all to raise that up. And it's actually a balance where the torque 1 equals torque 2. That's the balance that it will achieve. So that means the force on side 1 times the perpendicular distance on side 1 is equal to the force on side 2 times the perpendicular distance on side 2. So if I want to find the force I need to put in to solve that for force 1, and the force I have to apply to lift it is equal to the force of the thing I'm trying to lift times this distance divided by this distance. So if this distance is longer, I'm dividing by a bigger number. the force I put in is smaller than the force I'm lifting. And that leads to the famous, I can't remember which ancient Greek said this, but the famous quote of, give me a lever long enough and an appropriate fulcrum, that is an appropriate thing that I can put it against, and I'll move the world. Because all you have to do is have a long enough distance so that the distance from the world to the fulcrum is really tiny compared to the distance from here to where you are, and you could use a really small force to move the world. But then again, how much would you move it? If I move this a distance of, what would you say, 10 inches, that over there only moved a distance of about 6 inches. So it didn't move as far, but it took less force. And we can calculate the work. Work is force times distance. Take the distance that went up times the force there. That should equal the distance this went down times the force here. So the work in is equal to the work out. So all of this, what was the point of the simple machine?
To lower the force needed.
Okay, wow. Gaby's like on top of things. To lower the force needed. We do the same work. You don't get something for nothing. But you can do that work with less force. What do you have to have more of if you're going to have less force? Work is force times distance, so I'm going to have more distance moved to do the work. Less force, more distance. Now I want to make a point here. Torque is force perpendicular times distance. Work was force times, I'm going to put delta x just so we realize this is motion with the work. And it's motion parallel to the force. For torque, that's the lever arm distance. It's not the distance it moves. But they both have equations of force times distance, and it can be really confusing. What were the units for work? Joules. Unit of force is a newton, unit of distance is a meter. A newton times a meter we said is a joule. Well, what's the unit for torque? Okay, force is a newton, distance is a meter. We never ever say joules for torque. Even though it's a newton times a meter if it's work or torque, the joule is exclusively reserved for energy. So the people who asked, two people asked the question about what is the joule the unit of, and it's correct, it's work or energy, not torque, even though newton meter would be unit for both torque and work energy. So that unit thing is kind of confusing.
So what do you put?
You put newton times meter. Or if you're using it in the imperial system, foot pound. As opposed to, other units we use are horsepower, or, for work or for energy, but not for torque. Okay, the efficiency of a simple machine is the work done by the machine divided by the work you put in times 100%. That is, it's 100% efficient if the work done is equal to the energy you put in. It can't be more than 100% efficient. You can't get more work out than you put in, but you can have a frictional loss that lowers that efficiency. I'll end today with sources of energy. Now, this is a really important topic. What do we use for energy in our lives? Yeah, I drive an automobile. Standard, it's a Nissan, it's a Nissan Altima. Not a hybrid, not a electric. What am I using for the energy for that? I'm using gasoline. I am burning gasoline, converting chemical potential energy into mechanical energy. Now, if I had a Prius, then what kind of energy would I be using? Electric. But we have to go back. Where do these energies come from? Where did my gas energy come from? Okay? Gas, fossil fuels, they find oil, they refine it. Where's that oil come from? Back in the day, some animals got buried and got compressed and their bodies decomposed and made this oil. And so this oil used to be animals. Where do the animals get their energy from?
The plants that they eat.
The plants that they eat. Now, if it was a carnivore, they got it from the animals that ate. But those animals eventually had to get it from the plants they ate. You can't go forever in a carnivore cycle. Came from the plants. Where does it come from? The plants? The sun. So the sun is ultimately the source of energy for fossil fuels. Electricity. Where's our electricity come from? For most of us, it's from burning fossil fuels. So we'll go down the same path. We also have things like solar energy, where we are directly harvesting energy from the sun. It turns out the sun is over 99% of the energy budget of the Earth. All the energy we use comes from the sun ultimately, except for a very small amount, less than 1%, that comes from radioactive decays. So the sun is basically our ultimate source, but we can take that sun energy and get it different ways. We can get it with a solar cell that is directly taking the energy from the sunlight and turning it into electricity. We can use a windmill. Windmills are taking air currents that are caused by the sun, by the radiation from the sun, the heating from the sun, and using an electric generator to convert that into electricity. We can use hydroelectric power, which is taking water. We have the hydraulic cycle. Water evaporates up into the sky, comes back down as rain. That rain can hit at higher elevations. We make the potential energy of the water in the high lakes and convert it into kinetic energy as it goes down, and use that kinetic energy to drive a turbine to produce electric energy. All of that is actually using sun energy in different ways.